course, we are out of the mathematics you could conceivably have previously seen at school and into the mathematics that you certainly haven't. So we will be dealing today, we will be starting to deal today with the algebraic formalism of quantum theory, where everything begins with a function and the result integral. Gosh, it is really busy out there. Begins with an integral and is described by partial differential equations, and the expansions that you will see for quantum mechanical objects are not expansions of vectors in other vectors, they are expansions of functions in other functions. So the topic of today is so-called metric function spaces. We will see in a moment what it is, but the way I want to structure it is on this side of the board I will have vectors and all the reminders of everything that you know about vectors, and on that part of the board we will be building the corresponding theory of functions. So vectors go here and functions go here. You probably remember the definition of a vector space. It was a set of vectors that had to satisfy certain conditions to be a space. So A is a space over some field F if first requirement that we had is that A had to be closed under the operation called addition. So for any A and B vectors belonging to A, their sum, A plus B, also had to be in A. Then we wanted to have it in such a way that multiplying a vector by a number from this scalar field also retained the vector inside A. So it has to be closed under multiplication by a scalar. So for any A belonging to our space, and for any scalar that is sitting in F, we must have alpha A also inside A. And this is trivially true, for example, for standard three-dimensional vector space, right? If you add two vectors together, you get a vector, and if you multiply a vector by a number, you still get a vector. But for example, if we look at these things and we say, okay, is the set of all concentration distributions in space? Well, it probably isn't, because there's no such thing as a negative concentration, right? If you multiply it by some numbers, you would no longer have a concentration. So there are objects in chemistry which are spaces, and there are objects which are not. And then, of course, this arithmetical operation, the addition and this multiplication here, had to obey certain properties. First of all, we must have for any A and B belonging to A, the addition operation must be what we call commutative. A plus B must be B plus A. B must be equal. It must also be associative. So it shouldn't depend on the order of brackets. Any A, B, and C belonging to A. It shouldn't matter in which order we add them. A plus B plus C. This way should be exactly the same as A plus B plus C that way. And again, trivially true for the standard vector spaces. And the same must be true for the multiplication by a scalar, for any A, and for any alpha in F. We must have alpha, and let's say not just alpha, but alpha and beta. Alpha, beta, A. This way must be exactly the same as alpha, beta, A, that way. And so on. So bracket opening rules with respect to addition and multiplication. So all bracket opening as per usual. You have the detailed list in the handout. Now, let us look at these properties and think about how we build the corresponding function object. Well, it turns out we don't actually need to do much because we can simply just copy these properties over. They also hold for functions. So a set A is a function space over F if. So that was vector space, and this is now a function space. So correspondingly, for any F and G belonging to A, the sum belongs to A. F plus G belongs to A. And for example, the set of all continuous functions will obey this property because a sum of two continuous functions is a continuous function. The same for differentiable functions, the same for certain other types, polynomials, for example. The sum of two polynomials is a polynomial. So you can see that there are functions that satisfy this property. 2 multiplication by a number, so for any function living in A, and for any scalar, for example, for any complex number, then alpha f is also in A. We can take a function, multiply it by a complex number, and the result is a function. We can add the functions in any order. This is just copied over. It is clear that addition of functions satisfies those properties. It is clear that if we multiply a function by a number and then by another number, we can do that in any order. That property is copied over. And then 6 is also obviously true. So we didn't actually have to put all that much effort to observe that function spaces are spaces from the formal mathematical point of view. The interesting things begin when we introduce the metric. Remember that we had the notion of the length of a vector and the angle between the vectors, and we had perpendicular vectors and so on. So what does it mean to have a length of a function and perpendicular functions and such like? So here we have metric. And one of the many possible kinds of metrics was the Cartesian metrics, the one that you have in the usual three-dimensional space. We have there a norm, and the norm of a vector was the square root of v1 absolute squared plus v2 absolute squared, and so on, where v1, v2, and so on are the elements of that vector. Notice that in the most general case, you have absolute squares. This is when we have complex numbers to make sure that the length is actually a positive real number, or strictly speaking, non-negative real number. So norm, by definition, is supposed to be such, and so these moduli ensure that the complex numbers actually disappear. And then, of course, the sum of modulus squares can never be negative, and so this is guaranteed to be non-negative as a result. And then we have a scalar product. The vector v and vector u, and that was a sum. In the general complex case, we take complex conjugate u. We have to conjugate v, we have to multiply the two vectors element by element, and then to sum up the result. And the corresponding expression for this, in terms of a sum, space it here, was the sum of v a absolute square root. Now, how would we extend something like this to a function? Well, notice here that we have a sum over all elements of that vector. We can view function as a particularly long and densely packed vector. So in a vector, things occur at discrete positions. In a function, they would occur continuously, and they would be enumerated by the function. And so, as you know, in the limit of very densely packed elements, the sum becomes an integral. And so we can try and introduce the corresponding metric here by just using the corresponding integral. So the norm of a function, for example f of x, will be the sum becomes an integral, and then we have the function absolute square f conjugate f will be the absolute square of f, so let's just write it like that. X absolute square dx square root. If f were to take discrete values, just like a vector does, then this would have become the sum again. And the scalar product of two functions. We would have the function, and the scalar product with the function g will be an integral f complex conjugate of x g of x dx. Now the integration limits here depend on the problem. Typically in quantum mechanics they would be from minus infinity to infinity, because the universe is at least approximately infinite in every direction. But occasionally you have things like particle in a circle where certain angles, for example, can only go from 0 to 2 pi. So the limits are problem dependent, and you will be given those limits, or it will be obvious what they are, but normally minus infinity to infinity everywhere. And of course, remember that for vectors, we had the norm of a vector was the square root of a product of a vector with itself. And the same is true for functions. If you put f instead of g here, we will have f star f, which is f absolute squared, and so the scalar product of the function with itself is still z square of the norm. Norm f is root f. Notice how the notation actually becomes identical after a while. Once you introduce this bracket notation, the reason Dirac introduced this notation as he was developing quantum mechanics in 1920s or so, was that actually the algebra is copied virtually identically from vectors to functions. Another interesting property here is the dimension of the vector spaces we were dealing with has always been finite. They were 3-dimensional, 4-dimensional, and so on. It is quite common for the spaces of functions to have infinite dimensions. So welcome to infinite dimensional function spaces. This is actually where quantum mechanics operates. So let us now go through a couple of examples of calculating these things and a couple of examples of sets that are spaces and not spaces. So one simple example would be polynomials. We say f of x is a naught plus a1x plus a2x squared plus a3x cubed, and so on. It is clear that when you add two objects like this together, the result is still a polynomial. When you multiply a polynomial by a number, its structure doesn't even change, so it is a polynomial. And then all of these additions and associativity and commutativity and the distributivity rules, they all apply. And so the space of all polynomials is a valid function space. Another valid function space is a space of solutions, of general solutions, to a linear ordinary differential equation. If you have something like this, dy dx f of x plus 2 equals 0, that's a linear differential equation, and if we have two solutions, f1 and f2, then their arbitrary linear combination would also be a solution. If we write something like this, alpha 1 f1 plus alpha 2 f2, and we plug it there, then the derivative will act independently on both of these functions. You will add 2 as a result, and the result will still be 0. Actually, we need it to be uniform, so plus 2f. If you put that, and these are 2 solutions, then any linear combination of the solutions will also be a solution. And then if you multiply a solution by a number, it's still a solution, and so on. Therefore, the set of all general solutions to a uniform ODE is also a space. I've already mentioned various physical quantities like pressure distribution across the sample. I have something like this. It's P, and this is X. And pressure might vary across the sample. However, pressure as a function of X, all possible such functions, P of X, would not actually be a space, because the moment I multiply by a negative number, which this requires to be possible, I will get negative pressures. Well, relative to atmospheric to some extent, you can say that perhaps negative pressures are not that outlandish. You can define at least a negative pressure, but it would be hard to define, for example, negative absolute pressure. So certain functions in chemistry, even though they are continuous and in other ways well behaved, are not in fact spaces, but certain functions are very notably wave functions and quantum functions. Let us calculate a few norms of functions. We will come to calculation of normal vectors. We will comfortable with the notion of vector box. So let us go into functions instead. If I have f of x equals 2x plus 5x squared, a reasonably complicated complex valued function for which we are told to calculate the norm f of x, and we are given a specific interval. X belongs to the interval from 0 to 1. That's the integration range. We want the norm of that function on that interval. From the definition, norm f is integral, in this case from 0 to 1. The function conjugate goes in first, 2x minus 5x squared. Then the function itself, 2x minus x plus 5x squared dx. And the whole thing is the square root. We multiply that up. Integral from 0 to 1, 4x squared minus x to plus, I think it is x to the 4th, if memory serves, then dx square root. You can all take simple integrals of polynomial functions, so I will skip the arithmetic. The result is root 23/15. This is actually something that passes for the notion of length of a function on a specific interval. And we will need that in a moment when we do function expansions. Another example, we can calculate the scalar product, that is effectively the cosine of an angle between two functions in some abstract infinite dimensional space. Cosine x, sine x, scalar product on an interval, because these functions are periodic, between 0 and 2 pi. So integral 0 to 2 pi. Cosine conjugate is cosine, it's a real function. Cosine x dx. That is 1/2 of the cosine of a double angle. So 1/2 integral 0 to 2 pi sine 2x dx. That's an integral over 2 periods of a periodic function, therefore 0. Interestingly enough, in an abstract infinite dimensional function space, cosine is perpendicular to sine. We will see a lot more examples of these trigonometric kinds of identities in a few moments. Okay, we have so far copied from the vectors the definition of space, we have kind of hacked the notions of the norm and scalar product to apply to functions like they did apply to vectors. We did a few examples. The next thing we need to copy over from the vector spaces are linear combinations. Linear combinations. The definition is exactly the same as for vectors. F equals alpha 1 G1 plus alpha 3 G2 plus alpha 3 G3 and so on. And if F can be expressed in such a form, then it is said that F is a linear combination of the functions G1, G2, G3 and so on. Much like we had it with the vectors, there can be linearly independent and linearly dependent sets of functions. So set G1, G2, and so on is linearly independent if no function in this set can be expressed as linear combination of the others. There's no way to say gk is equal to the linear combination of other functions in this set. So if we take a sum over all n that's not equal to k, essentially a linear combination of all the other functions except the case function, if there is no way to make such a linear combination, then a set G1, G2, and so on is linearly independent. And much like it happened for vectors, if the set G is linearly independent, then this expansion here is unique. Remember what we did next in our vector spaces? That was to introduce the notion of a basis set. Item on the agenda. If G1 and so on is linearly independent, and any F can be expressed in the following way. So, for any F belonging to our space, F is sum over K alpha K G. Then G is called the basis. And much like we had it with vectors, there were just the basis sets with no particular properties, and you may remember it was rather difficult to expand vectors in just any basis because you have to calculate too many scalar products. And there are basis sets which are particularly convenient because they are orthogonal and normalized. So our next step is to introduce for some normal basis sets on function basis. Set, basis set. Gk is orthogonal if exactly the same thing applies that had applied to vector spaces. We want to have all the functions perpendicular to one another. G, K, G, M is 0 when K is not equal to N. Furthermore, the basis is called normalized if the norm of each function there is equal to 1. Gn is 1. And the basis is called orthonormal if it's both orthogonal and normalized. Orthonormal is G and scalar product GK is equal to something called Kronecker symbol, delta and K. And Kronecker symbol K is equal to 1 when n is equal to K, and it's equal to 0 when n is not equal to K. Basically just the elements of a unit matrix. All of this, if I just put little arrows on top of the F and the G, would not have been in any way unusual. You have already seen this for the vector spaces. For function spaces, this is really important because what will happen time and again is we would be given some list of functions. For example, atomic orbitals in here, over G's in the AOs. The second and third years have already seen this procedure, and we would be told to build a molecular orbital as a linear combination of atomic orbitals, the so-called LCAO method. Linear combination of atomic orbitals, Hückel theory, and so on. So I can see the side of pain understanding in the father's eyes in there, because they've seen it already. Our job here is to create convenient mathematical infrastructure for making such expansions. If that's the s orbital of some hydrogen, and that's the p orbital of some carbon, and that goodness knows what, goodness knows where in the molecule, we would want to know which coefficients are here that makes the orbital that participates in some chemical bonding. All this infrastructure is there to enable us to do that in quantum mechanics. So let us therefore move to the topic that this is all was the preparation for. It's called function expansion. Let us say that we have a basis, some linearly independent functions G. Given a basis, G of K, and we will make it orthonormal. Find the coefficients in following expansion. And the expansion is exactly this. We will have f, for example, of x, but it could be of any number of variables, in which case all the integrals become multiple integrals. F of x is a sum over k alpha k g k of x. Fairly typically, in modern quantum mechanics, g's would be complex exponentials or sines and cosines, and f would be some molecular orbital. And we would like to find the expansion of that molecular orbital in that basis. Well, what can we do? Let us take a scalar product of this entire expression, both the left and the right hand side, with a particular function. So, gn. I'll take the scalar product of f with gn, and I'll take the scalar product of this sum, and therefore each of these terms with gn. So scalar product g and f will be the sum over k alpha k g and g k. So sum is linear, scalar product, you can take the numbers out. So this is what we have. But remember the definition of our basis set, it was orthonormal, And so most of these scalar products are actually zero. In fact, the only one of them that is not zero is when n is exactly the same as k. Remember this running reciprocal, right? When n is k, it's 1 and it's 0 in all other cases. So in this entire big sum, only one term actually survives, and that's the term when n is exactly the same as k. And even then, gn is 1. So we are only left with alpha n, which then produces a wonderful relation that alpha n is a scalar product of gn with f, which is a pretty extraordinary result if you think about it. If you are given an arbitrary system of functions, with the only condition being that they are orthogonal, and you are given an arbitrary function to expand in them, you can actually trivially calculate the expansion coefficients by taking the corresponding integrals. This is why I was teaching you to integrate so much. If they are functions of one argument, you will have single integrals. If they are functions of multiple arguments, you will have multiple integrals, and so on. But actually, the fundamental expression that generates functional expansions is very, very simple. Let us go through a few examples of this. Let's pick a couple of common basis sets, demonstrate that they are orthonormal, and then I think I've got an example of something being expanded. Let's take a look at cosines. We've already seen that cosine is mysteriously perpendicular to sine with respect to the scalar product that we have defined. Let's take a look at a system of cosines of various multiples of the same angle. So the system of functions that we will use is as follows. G m of x will be 1 over root I cosine nx. That is, g1 is cosine x, g2 is cosine 2x, g3 is cosine 3x, and so on. Our task here is to demonstrate that this basis is in fact orthonormal. That is, we need to show that the norm is 1 for all n, and we need to show that if we pick a cosine with an n and a cosine with a k, if n is different to k, then these two functions are perpendicular. Let us do that. Norm of gn of x will be 1 over pi, because they will occur twice under the integral 0 to pi cosine mx squared dx. We can take cosine squared and we can expand it as a function of a double angle. So, reminder, cosine squared x is 1/2 1 plus cosine dx. So this becomes 1 over 2 pi integral 0 pi 1 plus cosine 2nx dx. N is an integer. We will have an integral over a period of a harmonic function, so the integral over the cosine will simply vanish, and we are left with the integral of 1. So that is 1 over 2 pi. Integral from 0 to 2 pi, 1 dx will also be 2 pi. So we have 1. And that is the norm of that cosine. Notice that if it wasn't for this little multiplier in front, we would have had a different norm. We divided our way root pi, it became a pi there. If it wasn't for this 1 over root pi, this would have been pi. This multiplier, that the second years have already seen, is called the normalization multiplier. It makes sure that the function has the unit norm, because that is required by the expression that we have derived over there. If we didn't have a unit norm, it would have been more complicated. Let us now demonstrate that cosines with different values of n are actually orthogonal. Scalar product Gn with Gk, where n is not equal to k. This will be an integral, again 1 over goes in front, cosine and x, cosine x dx from 0 to 2 pi. Opening the book, looking up the horrible trigonometric expression, 1 over 2 pi integral 0 to 2 pi of the horrible trigonometric expression, which in this case is cosine n minus k x plus cosine n plus k x dx. If n is not equal to k, then this is integer and that is integer. It's an integral over a complete period or over several periods, depending on which numbers we have in here, both are 0. Which leads to an interesting conclusion that actually any integrable function, so long as it's even, right, because all the cosines are even with respect to the change of sign in the argument, so any even function f of x has the following expansion over n alpha n cosine nx, which is a pretty non-trivial statement to prove. And in fact, the coefficients alpha n are just integrals of f of x with their corresponding cosines. If we want them conveniently normalized, probably I'd say 1 over pi should be there in front, just for convenience. And this is what happens with atomic orbitals. They would normally be some function of x, functions of x, y, z. They are either designed to be or assumed to be orthogonal, and then your molecular orbitals are expanded in them, and you are calculating these coefficients by taking the scale product, and then subsequently you are working with the vectors of these coefficients, which is where those vectors and matrices are in quantum mechanics. Okay, so let us now go, let's say, through a particular context that you would realistically have in your second year. Some radical. If you take propyl radical, or propyl it's called, because of the plus in it here. You know that you have p orbitals on it. P1, P2, and P3. These orbitals will be functions of x, y, and z. You can see already that things are getting more complicated because you do not have single integrals but triple integrals. And then what Huckel's theory particularly does, it says, okay, these p's would have scalar products, for example, p1, p2, and it is fairly clear that if I multiply that function by that function and take an integral, that the integral would not, in fact, be 0. But certain approximations within molecular orbital theory say, okay, this overlap integral is sufficiently small, so let us assume that that is 0. We can easily normalize these three functions, at which point any other function, a linear combination of that, f of x and y and z, will be alpha 1 p1 plus 2 p2 plus 3. And you would normally be asked in your second year to find such coefficients, alpha 1, alpha 2, and alpha 3, as minimize the total energy of this molecule. And that is another integral that they will introduce. So imagine, I will not go further into that, this is Marina Karavetto's job in your second year, but you can see how all of this, and actually everything I've taught you so far, comes home. You will have a function space on which norm and scalar product would be defined, or in this case assumed. You will be asked to find a linear combination of these called a molecular orbital such that minimizes the energy, and what you would then have to do is to paste this function, differentiate the result with respect to alpha 1, alpha 2, and alpha 3, and find the minimum of the energy function which will be given to you in the three-dimensional space of the coefficients in this functional expansion. So there's your differentiation, there's your integration, there's your functional expansions, and that's the optimization theory for you, all in one package, and that's the simplest program. So that is the applications, and we will get a bit closer to the associated mathematics in the second lecture. Okay, so the summary of today is we have taken what you already knew about vectors, and we have copied it literally over to the functions. We have introduced the notion of function space, then we have adopted the metric, except we had replaced sums with integrals because our functions are not discrete but continuous. The metric space is called the Hilbert space actually, and this is where wave functions and orbitals live in mathematics. We used the norm and the scalar product then to define the notion of orthogonality for functions and the notion of norm length on function spaces. We introduced linear combinations of functions and the corresponding basis sets. And we observed that if we require our basis set to be orthogonal and every function in it to be normalized, then the task of expanding any function at all in a complete basis of the particular space is actually trivially simple, because you simply need to take the corresponding scalar product, and this is in fact exactly the same as what you had to do for vectors. If you were expanding a vector f as a linear combination of some orthogonal and normalized vectors g, you would have been taking these scalar products, and you in fact were taking them in your workshops. At the level of notation, at the level of this bracket notation, there's absolutely no difference between functions and vectors, but of course once you go inside of what this bracket actually means, for functions it's an element-wise product and the sum, and for vectors it's an element-wise product and the sum, and for functions it is an integral of the corresponding product. Okay, so these are the metric function spaces, and we will